Hey guys, we're going to continue our video lessons on rates of reactions. And in this video, we're going to focus on how the temperature affects the rate of reaction. And I'm going to give you three imaginary trials or reactions, and everything is the same in these three containers. The number, amount of reactants, the pressure, the volume, whatever, they're all the same except for one condition or one factor, which is the temperature. So in this container, we have the temperature of 10 degrees. This container is 50 degrees, and the last container is 100 degrees. So before we go into use the collision theory to explain how all these particles and reactants react to form products, and how we're going to graph them onto our diagram here, we're going to discuss about kinetic energy, all right? Kinetic energy and how kinetic energy affects the kinetic movement of particles or reactants or substances. So we know that at very low temperatures, substances tend to be in solid phase, all right? So there's going to be jiggling going around between the particles in that solid phase, all right? It's just moving around, jiggling, and it's not really, flowing or whatever. It's stuck together, all right? Now, what happens is that when you increase the temperature, you're going to cause the jiggle to get more and more violent, and eventually the electrostatic force between the particles is going to rip off, and then you're going to get it moving more slowly, although it's still quite close together, and it's going to form change to its liquid phase. And so that's what happens when solids become liquid, all right? And when you increase the temperature again, you're going to increase the kinetic energy in that system, and then the thing will jiggle so violently until it ruptures. And then some of the substances will eventually make its way to the surface of the liquid and then evaporates, all right? So that's what happens between particles in the solid, liquid, and gaseous phase. So we got that down. So now that we understand that, we can use that in terms of how temperature affects the rate of reaction. So here we go. At 10 degrees, right? It doesn't really matter what the substances are, what the reactants are. It's just an orange substance and a reactant, and a blue reactant. I'm just going to call them particles, all right? So it's not going to travel very much. On average, it's going to move in this, on average, it's going to move this much in the reacting container, all right? Now, the reason why I say on average is because sometimes you get one or two really fast ones, and then the others are going to move even slower. But on average, for the entire system, that's the amount of kinetic energy and amount of movement of these particles in that 10-degree reaction container, all right? So reaction is still going to happen. There's still going to be a collision, although not very quickly. More on average, it's going to be about this quick, all right? I'm just trying to illustrate that. But occasionally, one or two of them will have a high kinetic energy. And when it collides, it may form products, but most of the time not. But somehow, one or two might start reacting with each other over a period of time. And so when we plot that onto our graph, we're going to see that, okay, the products are still like the same, still going to be, maximum amount of products is still going to be this much. But the rate, again, is low, all right? So you don't see a lot of change in the reaction. The rate is low, and it goes lower around here, and then eventually a plateau off as soon as all the products are made, all right? So there you go. That is the collision theory of temperature affects the rate of reaction. And what if we increase the temperature, all right? I'm just putting 50 degrees. It doesn't have to be 50 degrees, but I'm just saying that just for simplicity's sake. And so the kinetic energy in this system is going to be a lot more than the one in the 10 degrees. So I'm just drawing on average the amount, the movement of these particles, all right? So it's a lot more on average. So on average also, you get more particles moving more quickly, all right? The kinetic energy is a lot more quickly. And you get more hard banging collisions, and some of it will react, okay? And so definitely here, when we increase the temperature, we also increase the rate, at least the initial rate of the reaction. So here I go, I draw the curve, and it's going to plateau out again as usual. And the amount of products made is the same. So here you go, that's your graph where you'll have a higher initial rate of reaction, and it plateaus out as more and more products are made and less reactants are available, and then it will plateau off when all the products are made and no reactants are left. So what if I increase the temperature again to 100 degrees? So here, the kinetic energy is definitely a lot more, okay? So I'm just randomly drawing things left and right. Okay? There's definitely a lot more kinetic energy, and it's moving around a lot more violently. So definitely there's a lot of more hard banging collisions, and therefore the chances of successful collisions do increase in a shorter amount of time. And so what you get is when you plot this thing, after you collect all your data, is you get a higher initial rate of reaction, and it quickly plateaus off, and you produce the same amount of products. Okay? So there you go. The difference in the three rates of reaction depending on its temperature. So how do we generalize this? And this is something that you have to kind of know, especially for your exams, is that generally when you increase the temperature, so let me lower down the video so you can see what's down there. As you increase the temperature, there you go, the kinetic energy of these particles also goes up. Now I didn't write it down here, but you should know that. Also increase. So resulting in more collisions and also resulting in more successful collisions. Alright? Therefore you have higher rate of reaction. The rate at the beginning of the reaction should always be high because there are more reactants available, and as the amount of reactants decreases as the reaction goes on, the chance of successful collisions will also decrease. However, the total amount of products will always remain the same no matter what conditions, no matter what temperatures you have set for your reacting vessels. So that's a quick snapshot on how the effects of temperature on the rates of reaction.